All right, sorry about that little glitch there. I was there for a minute and then froze up, so I had to do a second recording. Apologies for that. So we were talking about divisibility tests for 3 and 9, and what I want to do is take a moment and kind of say, I'm pretty sure I'm going to give you an exam problem that says, can you prove that this is true for a particular number or for just a generic 4-digit, 5-digit number. So the 4-digit number proof is listed here, but I wanted to talk about it and show it to you in a way that I think might work better visually. Okay. So what I want to do is go back in class. We talked about the base blocks. Those were blue. You might remember them. And so we had little tiny base blocks look like that. Then we had longer base blocks kind of look like this. Then we had ones that look kind of like this. And then we had 3-dimensional ones, and I have no idea if I'll be able to draw these because it would look something like this. And then kind of like this. So we had that kind of 3-dimensional one. Okay. There we go. All right. So these are the different shapes that you have in, and we'll call this base 10 because we can do this in base 10. Honestly, you could do a lot of divisibility tests in other number bases. They may not look the same just because the numbers don't even look the same. Okay, so this is base 10. So we're going to take a number that would be, let's say 1,354. Okay. So what I want to do is kind of show you why using kind of these shapes, it either is or is not divisible by by 3. So what I'm going to start off with is kind of making the number in these blocks. Okay, so I have 4 of the little ones. Then I have 5 of the rods, right? And let's see, can I paste? No, it's not letting me paste. Okay. I'm using Zoom whiteboard, so it's not quite the same as some of the other ones. And again, you have to imagine these are, of course, all exactly the same size, but I need 5 of them. Okay. And then, there we go. And then I need 3 of these shapes. So I'm going to use the one that's up there. Here's another one. And then I'll put one maybe up at the very top. Let's see here. Can I move all of these down a little bit? There we go. Okay, so I'm just trying to make that last shape, and it was running out of space a little bit. Okay, so there we go. There we go. 3 of those, and then 1 of the big ones. Okay, so now as you picture this, I want you to just kind of picture. Oops, let me erase the ones that I don't need. So I don't need those. And this one, I'm going to move down a little bit. Okay, so here it is. You can visually see now 1,354. Is it divisible by 3? Very hard to kind of see if it's divisible by 3. But what you do is take things that are divisible by 3 and kind of chunk them out. So if I want to make a larger process, I don't want to say there's 4, so I could take a group of 3 out right now. You could, but let's leave the 4 alone temporarily. Now look at each one of these pieces. Each one of these is a rod or a long, and they have 10 little blocks. So if I was going to kind of make one up here, just kind of show you, right? 1, 2, 4, 5, 6, 7, 8, 9. Okay, and then I may have to, yeah. Let me just redraw that. That was that was pretty bad. So this time I'm going to draw it by doing it with just little blocks added on. So there's 1, 2, 3, and this is how you would make that kind of rod, is you'd have 10 of these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So now what we're doing is, as we make groups of either 3 or 9, because again, both of those are divisible by 3, what I would do is I would try to shade those. So I'd say, okay, well here, this chunk right here is a group of 9. Now, again, you could do this if you wanted to do this for 3. You would say, well, this is a group of 3, this is a group of 3, and this is a group of 3. So again, 3 groups of 3 makes up 9. So that's not a huge issue there. But notice what you have then is you have 1 left over. So from this first piece right here, I'm going to have 1 little box left over. So I'm going to draw that there's 1 little box left over. And again, the whole rest of it is perfectly divisible by 3. So I don't have to really focus on that. Guess what? The next one next to it also has one little box left over. The one next to it has one little box left over. The one next to it has one little box left over. So see what you're getting at is basically almost this entire chunk of all these different pieces, almost all of them are completely divisible into chunks of 9, which means they're divisible by 3. So what I have is these little pieces that come off the end of each one. So now if you think about that, that's basically all they are is little ones now, right? So that leaves 5 ones. I already had 4 ones. That's okay. Now let's come over to the 3 groups of 100. And now just kind of remember, each one of these is composed of 10 of those rods. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There we go. A perfect drawing yet again. Okay, so now here comes the fun. If I do the same thing like I did before, what I can do is come in and I can indicate, hey, wait a minute. 9 of these break up perfectly. See that? So those are divisible evenly by 9 and 3. So I can kind of remove those from the battle. And then that leaves me with one long. Remember the longs, like up here, almost all of them breaks up into pieces as well. So I'm going to break almost all of that up into pieces, leaving me just one little tiny chunk. And that one little tiny chunk I would need to count. So there's one more right there. If I repeat that for the pieces above, I'd have one more little chunk in the corner here, and I'd have one little chunk in the corner up there. Now that is actually a little tiny cube. I know they're drawn a little bit larger, but that's just because my horrible art skills. So now out of all of these, see that's 300, used to be 300, but I have removed all the multiples of 3 that I can grab really quickly, and it leaves me with just 3 single pieces. And now I come over to the thousands place. And once again, the thousands place is composed of 10 of these kind of flats stacked on top of each other. So like I can think of going, okay, there's one of them. Here comes the second one. Here comes the third one. And I go all the way to the top. But basically, we know that I'm going to have 9 of those. And 9 of those evenly divides perfectly. So I just can be like, okay, get rid of that chunk right there. And get rid of this chunk on the side over. Oops, that's not going to work well. Unfortunately, I cannot draw a parallelogram with this. So I'm going to, can I do it with a diamond? Maybe. Oh, it doesn't look like it. Well, you get that whole side stack is all gone too. It leaves me one flat, but each flat we just saw can be broken down into all of these pieces, which again, at the very end of the day is going to leave me just one little tiny piece behind. And I can picture that piece being kind of up here in the front. Oops, I think I did the lighter one. I'll do it darker. There we go, right up here in the front. And that is how we can show that even this group of 1,000 that we had here, that group of 1,000, yeah, it's doable. I can break it down, and what remains then? This is the fun part, at least for me. Out of this entire 1,000, there's one little cube left. So I'm going to put one little cube down here. Out of this group of 300, you'll notice there are 3 cubes left. So I've put 1, 2, 3 little cubes down here. Here's the 50, but there's 5 little cubes left. So 1, 2, 3, 4, and 5. And lastly, 4 ones, so I can bring them down. And what that means, even though you had all these other pieces, all these other chunks, they become groups of 3 or 9 very quickly. And what you're left with is just all these kind of singles, which is the same thing as saying I have 1 of these, I have 3 more here, I have 5 more, and I have 4 more. So the way we check to see if the entire number is divisible by 3, because all of the green stuff that I've already shaded is good, is to just add the digits up. 5 plus 4 is 9, plus 1 is 10, plus 3 more, it gives me 13. That is not divisible by 3. So I would say 3 does not divide 1, 3, 5, 4. Now again, if you wanted to check it, you could say, well, wait a minute, here's 3, so that makes a group of 3. Here's another group of 3. Here's a group of 3 by themselves. And here's 1 over here and 2 more over here. That makes another group of 3, and I'm left with 1. So it doesn't go in evenly, doesn't divide. All right, so mathematically, I'll do the 3-digit proof. So a 3-digit number that looks like A, B, C in base 10, which again would look like A times 100 plus B times 10 plus C times 1 is going to look something like this. And the way you prove it, so this is my proof to you. So the way that I check a 3-digit number in base 10 is I could actually break this down and say that the 100 is 99 plus 1. That the 10 is 9 plus 1. And finally, the last digit is just times 1. And then the distributive property kicks in. Because the distributive property says I can actually rewrite this. So I distribute here, and I distribute here. And there's not really much to distribute. I'm just multiplying those. So that one's going to be the quickest of all. Okay, so now I have, what do I have? 99 groups of A plus A. I have 9 groups of B plus B. And I have this C. Oops, I wrote an equal sign there. I did not mean an equal sign. I'll just redo that quickly. Plus C. So then your goal, when you're trying to prove that 3 divides this thing or it doesn't divide this thing, is to regroup everything you have that is divisible by 3 that you know of. And those are what we know of. So if you take this first chunk and you take this second chunk, kind of bring them together, you get 99A plus 9B. Right? Plus, and think about what's remaining over here would just be all the single digits, A plus B plus C. So now you can factor a 3 out of this if you want, or a 9, because both go in evenly. So what you can say is 3 times 33A plus 3B plus A plus B plus C. So we know 3 divides this because of theorem 4-1. And so now all we have to do is check the next piece, and that is theorem 4-2A or B. So if it does divide this second one, then the whole thing works perfect. And if it doesn't divide, then the whole thing fails. So bring it down, and what we knew is this tells you what to check. If, and this is if and only if, so let me rephrase that. So 3 divides the big number, which we started with. 3 divides A, B, C in base 10 notation, if and only if 3 divides A plus B plus C. That's the 3-digit case right here. All right, so that's how you prove something. You can show it, hey, it doesn't matter which number you pick and I check it and it works. I'm telling you that any number you pick is guaranteed to work. Right, let's jump back over to the textbook. See what else we might have left for us today. Okay, so there you have it. And here they are doing the base 4 one. Looks very similar to what I have. You see all of the 9s here, and 3 divides that chunk of 9s, and 3. So now it's based on the A plus B plus C plus D. So it's 3 divides your big number if and only if it divides the sum of the digits. And that's how you get your test for 3 and your test for 9. So it's a decent amount of work. So I'm not going to lie about that. I think that's interesting to say is it is a decent amount of work to get that started. Once you have the thing you need to check, though, all you have to do is add the digits together. 1, 4, 2, 3, 8. So add the digits together. 1 plus 4 is 5. Here's another 5. That's 10. And this gives me 18. And so you just have to ask yourself, does 3 divides 18? Question mark. And the answer is, yeah, that's true. And if it's true, then that's where our theorems come in. Then 3 has to divide 14,238. which would be a real stickler if I had to go through and do all the work right there. So really cool stuff that we get to see as ways to shortcut the work we might have to do. Usually someone says, well, can you show what if I didn't have that tool? What if I had to do it longhand? You could still use the theorems and try to shorten some of your work. Let me jump down here with some white space. And so just, yeah, you just want to kind of think about it and say, well, what would it look like if I was able to do that? So take your 14,238 and say, does 3 divide this? And then take your 14,320 and divide out some chunks that you know work definitely. Okay, like 12,000, because 3 goes into 12, right? Plus 2,238, perfect. 3 doesn't go into 22, goes into 21. So let me take off 2,100 plus 138. And then does 3 divide this at all? Well, 3 divides 120 because it divides 12 again. Okay, so that works, plus 18. And I'd say, yeah, 3 divides this and this and this and this. Therefore, by theorem 4-2a, it divides the whole thing. It divides the whole thing. Now, there's another reason why sometimes you'll see me write it out like this. And the reason is if I do write it out this way, the actual division can be super fast. So like, does 3 go into 12,000? Yes. And it goes in 4,000 times. So now I've checked that one off. Does 3 go into 2,100? Yes, it goes in 700 times. Oh, got it. Does 3 go into 120? Yes, 40 times. And does 3 go into 18? Yes, 6 times. So if I needed to, I could demonstrate that 14,238 is actually equal to 3 times 4,746, because that's what we found. Super duper duper cool stuff. And a great way to be able to do some mental math. So here, this is not a bad example. So what you get is the store manager had an invoice for 72 calculators, but a couple of the digits, he couldn't read them. They kind of blurred out over time, but he knew it was 72 calculators. So that means this number has to be divisible by 72. If it's divisible by 72, that means it's divisible by 8, by 9, by 7. Oh, sorry, not 7. I don't know why I said 7. I see the 72 there and I said 7. But think about all the other things that can go into 72. So 72 is 9 times 8. Yeah, I was not thinking 7. But then you can cut this one in 3. So this is 3 times 24. You can think of it as go the other direction, right? 18, double that, times 4. So all of these things have to work. It's 2 times 36 and so on. So you get a lot of options here. Those are all the things that have to divide. So when you see something like this, you could say, well, wait a minute. 72 calculators, it has to be divisible by 2. So that tells you the last digit has to be even. I also know it has to be divisible by 4, which means the last 2 digits have to be divisible by 4. That doesn't give us a lot of options then, because if you're looking at 9 and a blank space and it has to be divisible by 4, that's like 90 something. Well, that's 80 plus 10 something. And so what things end here that are actually divisible by 4? So it doesn't give you a lot of options. It's got to be like a 92 or a 96. Okay, because that would be a 12 or a 16. So I have 92 and 96 at the end. And then up in front, I know it has to be divisible by 9. That means the sum of the digits has to work out. Perfect. Let's see here. What else? That's divisible by 4. Ooh, it has to be divisible by 8 as well. Okay, so that might help us. So 7, 9 blank has to be divisible by 8. Let me come to the other side. 7, 9 blank has to be divisible by 8. I got to think about this. Oh, here's a good one. 790 something is really close to 800 minus another multiple of 8. So 800 is divisible by 8. 8 is divisible by 8. So 800 minus 8 would have to work, which means it has to be 792. Aha. So if you're doing a detective job, this is the way to do it. I now know it has to be 92. And the first digit up here, I don't know what that is yet, but I do know it has to be divisible by 9. So if I add all the digits up, and I'm going to put a little symbol in here for capital A, then I know that A plus 6 plus 7 plus 9 plus 2, that has to be divisible by 9. Let me add everything up here. So 9 plus 2 is 11. 11 plus 13 is 24. So I have 24 plus A, and it has to be divisible by 9. So 9 does not divide into A at all. But I know that 9 times 3 is 27, so that lets me know that the first digit would have had to have been a 3. And if I add 9 to it to get to my next 9, or 12, but it's a single digit, so it can't. So I am actually able to conclude that I can figure that out even though I don't know anything else. So pretty quick. Pretty quick. All right. And super cool too, because like, oh, I can solve problems that probably usually be like, I don't know, I just have to guess. We don't have to guess. Now we know. All right, so coming forward, you do have a divisibility test for 11, which is a super fun one with 11s, because 11s turn out, instead of always being one below, like groups of 9 are always one below, this one is either one below or one above. So one below, one above, it alternates. And so what you get is this really cool pattern where you can kind of do all the odd digits, add those, do all the even digits, add those, and then you find the difference between them. So it actually is a difference, not a sum. And your test for 6. And this is a good one to kind of think about, because your test for 6 is a little bit different. It has to be divisible by 2 and 3. And so be really careful with this, because sometimes your divisibility tests will overlap. We just saw 72, which is equal to 8 times 9. So we could check 8 and 9 because they have nothing in common, no factors in common. But if we had something like a divisibility test for 6 and for 12, that 6 times 12 is 72. If we checked, does 6 work and does 12 work, they both might work, but that doesn't mean the entire thing is divisible by 72. And the reason is, it goes back to those Venn diagrams. Because what happens is 6 and 12, they share a common factor. So you've already tested that factor once, but you didn't check it repeatedly. Okay. So as an example, I need a number that's divisible by both 6 and by 12, but is not divisible by 72. Well, here's kind of a short one, 24. You see 6 divides 24 and 12 divides 24, but 72 does not divide 24. Okay. So that's why when you see two numbers and the two numbers multiply to give you the larger number you're looking for, you can't just go and pick and say, oh, I just check both of those. That's not how it works. You got to make sure there's nothing in the intersection. So this has to be blank. And if you look at between 8 and 9, 8 is 2 times 2 times 2, and 9 is 3 times 3. So there is nothing in common. It would work just fine. And that's what they do for 6. If you factor 6, you get 2 times 3. Those have nothing in common. So you can use that as a divisibility test. And so, yeah, this is pretty typical of kind of a test question. I give you a massive number, so massive that your calculator probably won't be able to tell you whether it works or not. And that's the goal, because it doesn't matter whether your calculator can tell you or not. So then you can look to see, is it divisible by 2? Remember, the test for 2 is the last digit. It is not divisible by 2. Test for 3, that means I add all the digits up. That's going to take a little while here, but remember, that's the same as a test for 9. So you get 2 of them out of the way at once. And again, if it's divisible by 2 and by 3, then it's guaranteed to be divisible by 6. But we showed it's not divisible by 2, which means it's not divisible by 6, and it's not divisible by 8, and it's not divisible by 10, guaranteed. So once you rule one of these out, then all the things that multiply there are going to fail you. It's definitely not divisible by 5. We can see that. That's the last digit. And 11 would be alternating. So 57729 364 583. So when I say alternating, I mean take every other digit and add those together, and then do the same going the other direction with the ones that you left off. So 8 plus 4 is 12, plus 3 is 15. See here, 16, 17, and 7 is 24. Okay, so now I have 5 plus 7 is 12, plus 9 is 21, plus 6, 27, and 27 plus 8 is 35. And what you do is you find these two numbers, which is those sums, and you can just subtract to get a number that has to be a multiple of 11. And 11 is a multiple of 11. So that works out really nicely. Phew. There we go. Let's see here. Oh, here's Abby's magic trick. All right, I'll let you go through and figure that little trick out. I think that's the end. We're into the homework. So sorry for the two-parter on this, but I do think it's kind of an important one, so I want to make sure I didn't leave you hanging. All right, hope that helps. Off you go.